Black holes are not the strangest thing gravity can create. That sentence alone should stop you cold. For decades, black holes have occupied the darkest corner of human imagination, the ultimate endpoint, the point of no return, the place where physics breaks down and the universe stops making sense. They are, by almost universal consensus, the most extreme objects in existence. And yet, there is a class of theoretical object that challenges that assumption at its foundation, not by being bigger or denser or more violent, but by being fundamentally, philosophically different in a way that forces us to reconsider what we think we know about space, time, matter, and the nature of reality itself. They are called Gravastars. The name sounds almost gentle. A portmanteau of gravitational vacuum condensate star, a mouthful that physicists compressed into something more manageable. But do not be deceived by the name's brevity. The implications of gravastars, if they exist, are among the most unsettling in all of modern astrophysics. Because a gravastar does not simply replace a black hole in our models. It challenges the very concept of a singularity. The infinitely dense, infinitely small point at the heart of a black hole where the known laws of physics collapse entirely and produce mathematical nonsense. Where general relativity, the most precisely tested theory in scientific history, simply stops working. Stop and consider what that means. A theory tested to 11 decimal places of precision. A theory that predicted the bending of light around the sun, confirmed during the solar eclipse of 1919. A theory whose equations were used to detect gravitational waves from colliding black holes over 1 billion light-years away, where 1 light-year alone equals approximately 9.5 trillion kilometers, a distance so enormous that if you tried to drive it in a car at 100 kilometers per hour without stopping, it would take you over 10 billion years just to cross a single one. A theory that underpins GPS satellite technology, without which your navigation apps would drift by kilometers every single day. That theory, at the center of a black hole, produces an answer that cannot be physically real. It outputs infinity. And infinity in physics is not an answer. It is a symptom. It is the universe telling you that something in your model is broken. Gravastars are the attempt to fix that break without abandoning everything we know. The story begins not with gravastars, but with the long, complicated, deeply human struggle to understand what happens when a star dies. Not a small death, not the quiet cooling of a white dwarf, a stellar remnant roughly the size of Earth, settling into a billion-year fade. Not even the dramatic, luminous violence of a supernova, which at its peak can briefly outshine an entire galaxy of 200 billion stars. The death in question is the one reserved for the most massive stars, objects anywhere from 10 to 100 times the mass of our own sun, or beyond. Stars so massive that the weight of their own outer layers, pressing inward under gravity, is held up for millions of years by the pressure of nuclear fusion happening at their cores. Hydrogen fuses into helium. Helium fuses into carbon, carbon into oxygen, into neon, into silicon. Each stage burns faster and hotter than the last. A star the mass of 20 suns might spend 8 million years on the main sequence burning hydrogen, then only a few thousand years burning helium, then a matter of centuries burning carbon, then a single year burning silicon. And then, at the end of that chain, comes iron. Iron is where fusion stops paying dividends. Every element up to iron releases energy when it fuses. Iron does not. Fusing iron consumes energy rather than releasing it. And so, in a process that takes less than a second, the iron core of a massive star reaches a critical mass, approximately 1.4 times the mass of the sun, compressed into a sphere roughly the size of a large city, and it collapses. The core falls inward at roughly 23% of the speed of light, which is 69,000 kilometers per second. To understand that number, consider that the circumference of the Earth is approximately 40,000 kilometers. In 1 second, the infalling core travels a distance equivalent to 1.5 laps around the entire Earth. The collapse happens in a fraction of a second. And then the shockwave bounces back outward, and the supernova begins. What is left behind, in the most extreme cases, is the object at the center of our entire discussion. A region of space where matter has been compressed beyond the density of an atomic nucleus, which itself is already incomprehensibly dense, with a tablespoon of nuclear density matter weighing roughly 2 billion tons. into something far smaller, far stranger, and by the mathematics of general relativity, infinitely dense. A singularity, a black hole. The boundary surrounding that singularity is what physicists call the event horizon. It is not a physical surface. There is no wall, no membrane you could touch. It is simply the mathematical boundary beyond which the escape velocity, the speed required to leave that region, exceeds the speed of light, which is approximately 299,792 kilometers per second. Nothing that we know of travels faster than light, so nothing escapes. Not matter, not energy, not information. The event horizon is a one-way door written into the geometry of space-time itself. For most of the 20th century, this was the accepted model, refined and built upon by some of the greatest minds in physics. Carl Schwarzschild, who derived his famous solution to Einstein's field equations while serving on the Eastern Front during World War I in 1916. John Archibald Wheeler, who popularized the term black hole in 1967. Stephen Hawking, who in 1974 proposed that black holes are not entirely silent, that quantum mechanical effects at the event horizon cause them to radiate energy at an extraordinarily slow rate, a process now known as Hawking radiation. The model was elegant. Terrifying, but elegant. A dead star collapsing past its Schwarzschild radius, sealing itself away behind an event horizon, dragging space-time itself inward toward a point of infinite density. Settled science, consensus physics. And then, in 2001, a physicist named Pavel Mazur and a cosmologist named Emil Motola published a paper that asked a question almost no one in the mainstream had seriously entertained. What if the singularity never forms? Not because something stops the collapse partway. That scenario was already known, and it produces neutron stars, objects so dense that a single teaspoon of their material would weigh approximately 400 million tons on Earth. But what if, at the very threshold where a singularity would form, the laws of quantum mechanics intervene in a way that general relativity simply cannot account for? What if, instead of continuing to collapse into infinite density, the matter undergoes a quantum phase transition, a fundamental change in its physical state, similar in principle to the way water becomes ice or a conductor becomes a superconductor, but occurring at the most extreme energies the universe can produce? What if at Manindetia, that boundary, space-time itself, becomes something else? Mazur and Motola proposed that the result would not be a singularity. It would not be an event horizon in the traditional sense. It would be a gravastar, an object with a thin shell of ultra-dense matter surrounding an interior, filled not with a singularity, but with a form of dark energy, the same repulsive energy responsible for the accelerating expansion of the universe on its largest scales, an interior where the geometry of space-time is inverted, where instead of infinite gravitational pull pointing inward, the quantum vacuum exerts an outward pressure that exactly balances the enormous weight of the shell above it. From the outside, a gravastar would be nearly indistinguishable from a black hole. The mathematics of its gravitational field would look almost identical. Light would curve around it the same way. Objects would orbit it by the same rules. The shadow it casts, the dark silhouette photographed by the Event Horizon Telescope in the galaxy Messier 87 in 2019, and in our own galactic center, Sagittarius A star, in 2022, might look essentially the same, nearly indistinguishable, but not identical. And in that razor-thin difference lives one of the deepest questions in physics. Because if gravastars exist, then there are no singularities. And if there are no singularities, then information is not destroyed when matter crosses the threshold. And if information is not destroyed, then one of the most contentious and unresolved debates in theoretical physics, the black hole information paradox, which has occupied and divided physicists for over 50 years, finds its resolution not at the edge of a black hole, but inside the alternative that replaced it. The universe kept a secret from us for billions of years. The black hole was never quite what we thought it was. The paper Mazur and Motola submitted in September 2001 was not, by any conventional measure, a revolution. It arrived quietly. No press conference, no headline in a major science magazine, no statement from a Nobel laureate. It was a preprint deposited in the Archive repository, the vast, publicly accessible archive where physicists post work before formal peer review. And it sat there, available to anyone with an internet connection and the mathematical background to parse it. Most of the physics community did not immediately upend their models. Most continued working within the established framework of black hole physics, the one that had been built, tested, and refined over 85 years. That is how real science often moves. Not in dramatic announcements, but in papers that sit at the edge of consensus and pull, quietly, until the ground begins to shift. What Mazur and Mottola actually proposed was grounded in a phenomenon already well understood in a completely different context: the Bose-Einstein condensate. In ordinary matter, particles behave individually. Each atom, each molecule, follows its own quantum mechanical trajectory, colliding and interacting according to statistical rules that, in aggregate, produce the behavior we recognize as solid, liquid, or gas. But under extreme conditions, temperatures approaching absolute zero, the coldest possible state of matter at approximately minus 273.15 degrees Celsius, something remarkable happens. Particles of a specific quantum type, called bosons, stop behaving as individuals. They collapse into a single collective quantum state. They become, in a meaningful physical sense, one object described by one wave function. The boundary between individual particles dissolves. This is a Bose-Einstein condensate, first predicted by Satyendranath Bose and Albert Einstein in 1924 and 1925, and first experimentally confirmed in a laboratory at the University of Colorado in 1995 by Eric Cornell and Carl Wieman, work for which they received the Nobel Prize in Physics in 2001. Mazur and Mottola asked a question that was, in retrospect, almost obvious once someone had the courage to ask it. If quantum phase transitions of this kind exist in ordinary matter under extreme cold, what happens when you apply the same logic to space-time itself under extreme gravitational compression? The answer they proposed was a phase transition at the threshold of black hole formation, not in the matter falling inward, but in the quantum vacuum itself. The vacuum of space is not empty. This is one of the most counterintuitive and experimentally confirmed results in all of quantum field theory. Empty space seethes with virtual particles constantly appearing and annihilating in pairs, with energy fluctuations at every point, with a ground state energy density that is real and measurable. The Casimir effect, the measurable attractive force between two uncharged metal plates placed extremely close together in a vacuum, is direct experimental proof that the quantum vacuum carries energy. The plates are attracted to each other because the space between them, being smaller, supports fewer vacuum fluctuations than the space outside them, creating a net inward pressure. This has been measured in laboratories. It is not speculation. Mazur and Mottola proposed that at the critical density, where a black hole would normally form, the quantum vacuum undergoes a phase transition into a new state, a gravitational Bose-Einstein condensate, in which the interior of what would have been a black hole is instead filled with a form of dark energy. The equation of state of this interior obeys a precise relationship: pressure equals negative energy density. That minus sign is the key to everything. In ordinary matter, pressure is positive. It pushes outward, resisting compression. In dark energy, the pressure is negative. It acts repulsively, pushing space-time apart. It is the same dark energy, described by the same equation of state, that cosmologists believe is responsible for the accelerating expansion of the observable universe. The same physics operating at the scale of the entire cosmos, Mazur and Mottola argued, also operates at the scale of a collapsing stellar core. The structure that results has three distinct regions. The innermost zone is the dark energy interior, a de Sitter space, the same geometry that describes the large-scale structure of our accelerating universe, where the cosmological constant drives expansion rather than collapse. The outward pressure of this interior exactly balances the inward gravitational pull of the shell surrounding it. No singularity forms, no event horizon forms. The second region is a thin shell of matter in an ultra-relativistic state, matter compressed to densities comparable to nuclear density, but existing as a coherent quantum object rather than a classical fluid. This shell is extraordinarily rigid. Theoretical estimates suggest that stretching it by a single meter would require energy on the order of a supernova, approximately 10 to the power of 44 joules, which is roughly the total energy output of our Sun across its entire 10 billion year lifespan. The third region is the exterior vacuum, indistinguishable in its gravitational behavior from the exterior spacetime around a black hole. The Gravastar has no event horizon. It has no singularity. It is, at its heart, a bubble of the quantum vacuum condensate, held together by the equilibrium between its dark energy interior and the pressure of its ultra-dense shell. Now consider the thermodynamic implications, because they are where the Gravastar model diverges most sharply from black hole physics in testable, measurable ways. Black holes, according to Jacob Bekenstein's work in 1972 and Hawking's derivation of black hole thermodynamics in 1974, carry entropy. Enormous entropy. The Bekenstein-Hawking entropy of a black hole is proportional to the area of its event horizon, not its volume. A fact so strange and so profound that it became the foundational motivation for holographic models of the universe. A black hole with a mass 10 times that of our Sun has an entropy of approximately 10 to the power of 78 in natural units. That number is so large it exceeds the entropy of all the matter that fell into the black hole to create it by many orders of magnitude. Where did the extra entropy come from? The answer involves the degrees of freedom hidden behind the event horizon, the information encoded in the precise quantum states of everything that ever fell in, rendered permanently inaccessible to any external observer. A Gravastar carries essentially zero entropy in its interior. The Bose-Einstein condensate state is, by definition, a state of minimum entropy. All the quantum degrees of freedom have collapsed into a single ground state, the way a perfectly ordered crystal at absolute zero has no thermodynamic disorder. The exterior shell has some entropy, but it is finite and calculable. The total is incomparably smaller than the Bekenstein-Hawking entropy of an equivalent mass black hole. This is not a minor technical detail. It is a fundamental diagnostic. If you could measure the entropy of an astrophysical object that looks like a black hole from the outside, and you got an answer consistent with near zero rather than the enormous Bekenstein-Hawking value, you would have strong evidence for a Gravastar. The challenge, and it is a severe one, is that measuring the entropy of a distant astrophysical object is extraordinarily difficult with current technology. The surface temperature of a Gravastar presents an equally striking contrast. General relativity predicts that photons climbing out of a deep gravitational well lose energy. They are redshifted. The deeper the well, the more energy they lose. For an object as compact as a Gravastar, the gravitational redshift of any radiation emitted by the shell would be extreme. Theoretical calculations place the effective surface temperature of a Gravastar at approximately 1/1000th of a degree above absolute zero, making it, in principle, the coldest object physically possible in the universe. Colder than interstellar space, which sits at approximately 2.7 Kelvin, the temperature of the cosmic microwave background radiation left over from the Big Bang. The Gravastar's shell would be colder than the universe itself, and yet, from outside, it would look, gravitationally, almost exactly like a black hole. The information paradox is where this distinction becomes not merely academic, but existentially critical to the foundations of physics. Hawking's 1974 calculation showed that black holes radiate, slowly, over astronomical timescales, but continuously. For a black hole with a mass 10 times that of the Sun, the Hawking temperature is approximately 6/1000ths of a Kelvin, and the evaporation timescale is approximately 2 times 10 to the power of 74 years, a number so vast that the current age of the universe, at approximately 13.8 billion years, is not even a rounding error. But the principle stands. A black hole radiates thermally, and thermal radiation carries no information. It is random. It is featureless beyond its temperature. If a black hole forms from a specific configuration of matter, a star with a particular chemical composition, a particular rotation rate, a particular magnetic field, carrying within its atoms the quantum mechanical history of billions of years of stellar evolution, and then evaporates into structureless thermal radiation, what happened to all that information? Quantum mechanics is built on a principle called unitarity. The total information content of a closed system is conserved. Quantum states evolve deterministically and reversibly. You can, in principle, run the equations backward and reconstruct the past from the present. A universe that destroys information is a universe that violates unitarity. And a universe that violates unitarity is a universe in which quantum mechanics is not the fundamental theory we believe it to be. Hawking himself for nearly 30 years maintained that information was genuinely lost in black holes, that this was a real breakdown of quantum mechanics, an exceptional case where the universe permitted irreversibility at the most fundamental level. In 2004, he reversed his position, conceding at the Dublin Conference on General Relativity that information is likely preserved, though the mechanism by which it escapes remained, and to a significant degree remains today, deeply contested. A Gravastar sidesteps the paradox entirely, and it does so without requiring any exotic modification to quantum mechanics. If there is no event horizon, there is no region from which information cannot escape. Matter that falls toward a Gravastar is absorbed into the shell. Its quantum state is encoded in the shell's physical configuration. When the Gravastar radiates, and it would radiate as any object above absolute zero must, that radiation is not the featureless thermal bath of Hawking radiation. It carries in principle the quantum imprint of everything the shell has absorbed. Information is not lost. The paradox does not arise. The cleanness of that solution is precisely what makes it so attractive to a subset of theoretical physicists, and precisely what makes others deeply skeptical. In physics, a solution that is too clean, that resolves too many problems at once without introducing new complications, earns scrutiny rather than immediate acceptance. Because to accept the Gravastar, you have to accept the quantum phase transition at the Planck scale, and that requires a theory of quantum gravity, a complete, mathematically consistent framework that unifies general relativity and quantum mechanics. That does not yet exist. That is not a small requirement. General relativity is a theory of geometry. That sentence is worth sitting with. Not a theory of forces, not a theory of fields in the way electromagnetism is a theory of fields, but a theory of the shape of space-time itself. Einstein's insight, formalized in his field equations published in November 1915, was that mass and energy do not pull on each other across empty space the way Newton imagined. They curve the fabric of space-time, and what we perceive as gravitational attraction is simply the path that objects follow when moving through that curved geometry. A planet orbits a star not because the star reaches out and grabs it, but because the star's mass has bent the surrounding space-time into a bowl-shaped geometry, and the planet is following the straightest possible path, a geodesic, through that curved space. Remove the mass, and space-time flattens. Add more mass, and the curvature deepens. The field equations that describe this relationship are 10-coupled, non-linear partial differential equations. They are among the most mathematically demanding objects in all of theoretical physics. Exact solutions, cases where you can write down a clean, closed-form answer, are extraordinarily rare. The Schwarzschild solution, derived in 1916, is one. It describes the space-time geometry outside a perfectly spherical, non-rotating, uncharged mass. It is exact, elegant, and deeply strange, because it contains within it the mathematical prediction of the event horizon, the Schwarzschild radius, equal to 2 times the gravitational constant, times the mass divided by the square of the speed of light. For an object with the mass of our Sun, that radius is approximately 2.95 kilometers. Compress all the mass of the Sun into a sphere smaller than 3 kilometers across, and an event horizon forms. For Earth, the Schwarzschild radius is approximately 9 millimeters, roughly the size of a marble. The entire mass of our planet, squeezed into a marble, collapses behind an event horizon. These numbers are not metaphors. They come directly from the geometry of Einstein's equations, and they have been confirmed to extraordinary precision by astrophysical observation. The problem, and it is a problem that has never been fully resolved, is what happens at the very center of that collapsed object. The Schwarzschild solution predicts a singularity, a point where the curvature of space-time becomes infinite, where the density of matter becomes infinite, where the equations return values that have no physical interpretation. In mathematics, a singularity in a solution does not necessarily mean the physical system is singular. It often means the coordinate system has broken down, or that the theory is being applied outside its domain of validity. Physicists treat the singularity at the center of a black hole as the latter, as a sign that general relativity, as a classical theory, cannot describe physics at those extreme scales, and that a quantum theory of gravity is required. Quantum mechanics operates by entirely different rules. At its foundation is the uncertainty principle, formulated by Werner Heisenberg in 1927. It states that the position and momentum of a particle cannot both be precisely known simultaneously. More precisely, the product of the uncertainty in position and the uncertainty in momentum must always be greater than or equal to the reduced Planck constant divided by 2. The reduced Planck constant is approximately 1.055 times 10 to the power of negative 34 joule-seconds, a number so small that the uncertainty principle is completely invisible in everyday life. But at the scale of atomic nuclei, it dominates everything. The Planck length, the scale at which quantum gravitational effects are expected to become dominant, is approximately 1.6 times 10 to the power of negative 35 meters. To visualize that scale, consider that a proton has a diameter of approximately 1 times 10 to the power of negative 15 meters. The Planck length is 20 orders of magnitude smaller than a proton. If a proton were scaled up to the size of the observable universe, approximately 8.8 times 10 to the power of 26 meters across, the Planck length, scaled by the same factor, would still be smaller than a grain of sand.
The singularity of a black hole exists, in the classical theory, at zero size, smaller even than the Planck length. This is why the singularity is understood to be unphysical. No theory that ignores quantum mechanics can be trusted at that scale. The Gravastar model proposes that quantum mechanics intervenes before the singularity forms.
But the precise mechanism requires understanding what happens to space-time geometry under the specific conditions of gravitational collapse, not just to matter, but to the quantum vacuum that permeates all of space. In quantum field theory, the vacuum is characterized by its equation of state, the relationship between its energy density and pressure. For ordinary matter, pressure is positive and proportional to energy density. For radiation, photons, pressure equals 1/3 of energy density. For dark energy, as characterized by the cosmological constant in Einstein's equations, the equation of state parameter, denoted by the letter W, equals -1. Pressure equals negative energy density. This negative pressure is what causes the accelerating expansion of the universe. It is a repulsive contribution to the geometry of space-time, acting against gravitational collapse on cosmological scales. Mazur and Motola's central argument is that at the threshold of black hole formation, the quantum vacuum undergoes a gravitational analog of a Bose-Einstein condensation, transitioning into a state described by exactly this equation of state, W equals -1, throughout the interior of the would-be black hole. The mathematics of this transition draws on results from quantum field theory in curved spacetime, a framework developed through the 1970s and 1980s by researchers including Hawking, Robert Wald, William Unruh, and Paul Davies. Unruh's result, published in 1976, is particularly relevant. He demonstrated that an observer undergoing constant acceleration in flat spacetime perceives the quantum vacuum not as empty, but as a warm thermal bath of particles, a temperature directly proportional to the acceleration. This is the Unruh effect, and it reveals something profound. The quantum state of the vacuum is observer-dependent. What one observer measures as empty space, another accelerating observer measures as a warm gas. The event horizon of a black hole creates an analogous situation. An observer hovering just outside the horizon must accelerate continuously to avoid falling in, and they perceive the vacuum near the horizon as thermal. This is the physical origin of Hawking radiation. But the Unruh effect also implies that the quantum vacuum near an event horizon is not simply empty space dressed up thermally. Its structure is altered by the extreme space-time geometry. Mazur and Mottola argue that this alteration, at sufficient curvature, drives a phase transition. The vacuum does not merely appear thermal, it reorganizes into a fundamentally different quantum state, one with a different equation of state, different thermodynamic properties, and crucially, different geometry. The interior geometry of a gravastar is described by the de Sitter metric, the same solution to Einstein's equations that describes a universe dominated entirely by a positive cosmological constant, with no matter and no radiation, only dark energy. The de Sitter metric has no singularity. It is smooth, regular, and geodesically complete, meaning any path through this spacetime can be extended indefinitely without hitting a boundary or a breakdown. It is, in a precise mathematical sense, the opposite of the Schwarzschild singularity, where the Schwarzschild interior curves spacetime toward an infinitely dense point. The de Sitter interior curves spacetime outward, toward expansion. The boundary between the de Sitter interior and the exterior Schwarzschild vacuum is where the thin shell of ultra-dense matter lives. This shell is described using the Israel junction conditions, a set of mathematical constraints derived by Werner Israel in 1966 that specify how two different spacetime geometries can be joined at a boundary surface without introducing unphysical discontinuities. The junction conditions require that the induced metric, the geometry measured by an observer living on the surface itself, be continuous across the boundary. They also specify the relationship between the discontinuity and the extrinsic curvature, the way the surface bends within the surrounding spacetime, and the energy-momentum tensor of the matter composing the shell. Applying the Israel junction conditions to the Gravastar boundary, Mazur and Mottola showed that the shell must consist of matter with a specific equation of state, one corresponding to an ultra-stiff material where the pressure approaches the energy density and magnitude. This is the stiffest form of matter permitted by causality, the condition that no signal can travel faster than light. In nuclear physics, this equation of state is associated with matter at densities above nuclear saturation density, approximately 2.3 times 10 to the power of 17 kilograms per cubic meter. A thimble, approximately 5 cubic centimeters, of matter at this density would weigh approximately 1.15 times 10 to the power of 12 kilograms, or roughly 1.15 billion metric tons. The International Space Station, by comparison, has a mass of approximately 420 metric tons. The stability of this configuration is not assumed. It must be derived. A shell of matter in equilibrium between an outward-pushing dark energy interior and the inward pull of its own gravity, and the exterior vacuum will oscillate if perturbed. Whether those oscillations grow, destabilizing the object, or decay, allowing it to settle back to equilibrium, depends on the detailed properties of the shell's equation of state. Mazur and Mottola, and subsequent researchers including Piero Martin Maruno and Matt Visser, have shown that stable configurations exist across a range of shell equations of state. The Gravastar is not inherently unstable. It does not require fine-tuning to improbable precision to survive. This is a critical result, because a theoretical object that can only exist for a fraction of a second before collapsing into something else is not a compelling alternative to black holes. The angular momentum of the system introduces additional complexity. The Schwarzschild solution describes a non-rotating black hole. Real astrophysical black holes rotate, often rapidly. The appropriate description for a rotating black hole is the Kerr metric, derived by Roy Kerr in 1963, which introduces a phenomenon called frame dragging. The rotation of a massive object literally drags the surrounding space-time along with it, forcing even inertial observers to rotate in the same direction as the mass. Near a rapidly rotating Kerr black hole, there is a region called the ergosphere, outside the event horizon, but inside the region where the frame dragging effect exceeds the speed of light. Within the ergosphere, nothing can remain stationary relative to distant stars. Space-time itself is rotating. Extending the Gravastar model to rotating configurations requires constructing a rotating analog, a Gravastar described by an axially symmetric geometry rather than the simple spherical symmetry of the original Mazur-Mottola model. This has been done in various approximations by Cecilia Cirenti and Luciano Rezzolla, and by other groups. The rotating gravastar retains its essential features: no singularity, no event horizon, a dark energy interior. But the mathematics becomes substantially more involved, and the stability analysis in the rotating case is considerably less complete than in the non-rotating case. One of the most powerful observational tools for distinguishing a gravastar from a black hole involves the behavior of the spacetime just outside the compact object, in a region called the photon sphere. For a Schwarzschild black hole, the photon sphere, the radius at which light can orbit in an unstable circular orbit, sits at exactly 1.5 times the Schwarzschild radius, or 3 times the gravitational radius. Photons at this radius neither fall in nor escape to infinity. They orbit perpetually, balanced between the inward pull of gravity and their own momentum. The photon sphere is directly related to the shadow of a black hole, the dark silhouette observed by the Event Horizon telescope. Because photons scattered just outside the photon sphere reach a distant observer and form the bright ring surrounding the shadow. A gravastar of the same mass has a photon sphere at essentially the same location as a black hole. The shadow it casts would be nearly identical in size, but the details of the light distribution in and around the shadow, the precise brightness profile of the photon ring, the absence or presence of certain features within the dark region, would differ between a gravastar and a black hole. These differences are, with current instrumentation, at the boundary of detectability. They may not remain there for long. On September 14, 2015, at 5:51 in the morning Eastern Daylight Time, 2 L-shaped detectors located in Livingston, Louisiana and Hanford, Washington, recorded a signal that lasted approximately 0.2 of a second. The signal passed through the Livingston detector first, then reached the Hanford detector 7 milliseconds later, consistent with the travel time of a wave moving at the speed of light across the roughly 3,000 kilometers separating the two sites. The detectors are the instruments of the Laser Interferometer Gravitational Wave Observatory, known as LIGO. Each arm of each L-shaped detector is 4 kilometers long. The signal that arrived that morning displaced the ends of those 4-kilometer arms by a distance of approximately 1,000th the diameter of a proton. That is not a typo. 1,000th of a proton diameter. To put that in perspective, a single strand of human hair is approximately 70 micrometers wide. A proton is approximately 1 femtometer, 1 times 10 to the power of negative 15 meters, in diameter. LIGO measured a displacement of approximately 1 times 10 to the power of negative 18 meters. The hair strand is 100 trillion times larger than what LIGO detected. This was, at that moment, the most precise measurement in the history of experimental science. The signal was a chirp. It swept upward in frequency, from approximately 35 Hz to roughly 150 Hz, over the course of approximately 0.2 of a second, then cut off sharply. The waveform matched, with extraordinary precision, the prediction of general relativity for 2 black holes in a final spiral, circling each other with increasing velocity, losing energy to gravitational radiation, spiraling inward until they merged. The 2 objects were estimated to carry masses of approximately 36 and 29 times the mass of the Sun, merging into a final object of approximately 62 solar masses. The missing 3 solar masses, approximately 6 times 10 to the power of 47 joules of energy, were radiated away as gravitational waves in a fraction of a second. For that brief instant, the power output of the merger exceeded the combined luminosity of every star in the observable universe. The event was designated GW150914. It was the first direct detection of gravitational waves. It confirmed a prediction of general relativity that Einstein himself had doubted could ever be measured. And then Cecilia Chiarenti and Luciano Rezzolla published a paper. In 2007, working at the Max Planck Institute for Gravitational Physics, Chiarenti and Rezzolla had already established that a rotating gravastar would produce a distinct gravitational wave signature during perturbation, a signature measurably different from that of a black hole of the same mass. The key difference involves what physicists call quasi-normal modes, the characteristic frequencies at which a compact object rings after being disturbed, the way a bell rings at a specific pitch determined by its shape, material, and mass. For a black hole, the quasi-normal mode frequencies are determined entirely by 3 parameters: mass, spin, and electric charge. This is the content of the no-hair theorem, the result, proven through contributions by Werner Israel, Brandon Carter, and Stephen Hawking between 1967 and 1972, stating that a black hole in equilibrium is completely characterized by just those three numbers. All other information about the matter that formed it is gone. The black hole has no hair, no additional features, no memory of its origin. A gravastar has hair. Its quasi-normal mode spectrum depends not only on its mass and spin, but on the detailed properties of its shell, its equation of state, its thickness, its internal structure. The ringing of a gravastar after a perturbation carries information about the composition of the shell. This is a direct, measurable, in-principle distinguishable prediction. When Chiarenti and Rizzola applied their analysis to GW150914, they found that the post-merger ringdown signal, the fading oscillation recorded in the final milliseconds of the LIGO detection as the newly formed object settled into its final state, was not consistent with a gravastar. The ringdown frequencies and damping times matched the Kerr black hole prediction with sufficient precision to rule out the specific gravastar models they tested. The paper was titled, "With Characteristic Scientific Economy, Did LIGO Detect Black Holes or Gravastars?" The answer they reached was black holes. This result was significant. It was not, as some popular accounts suggested, the death of the gravastar hypothesis. It was something more precise and more scientifically valuable. A constraint. An experimental bound. The specific class of gravastar models with the specific shell properties Chiarenti and Rizzola modeled was ruled out at the confidence level their analysis permitted. Other classes of gravastar models with different shell equations of state or different interior geometries were not ruled out. Science advances exactly this way. Not through single definitive experiments that annihilate theories, but through the progressive narrowing of possibility space, each measurement closing some doors while leaving others open, each constraint forcing theorists to refine their models or abandon specific parameter regimes. The gravitational wave detections that followed GW150914 added more data. By the third LIGO Virgo Cagra observing run, completed in 2020, the catalog contained 90 confirmed gravitational wave events, the vast majority consistent with black hole or neutron star mergers. The ringdown analysis of multiple events tightened the constraints on departures from Kerr black hole behavior. The no-hair theorem was tested, statistically, across dozens of events. It held, but the constraints have a resolution limit. Gravitational wave detectors measure the ringdown signal only over a finite time, with finite signal-to-noise ratio. The earliest portion of the ringdown, the first few milliseconds after merger, when any potential gravastar signature would be most distinct, is buried in the loudest part of the signal, where the waveform modeling is most uncertain. The precise quasi-normal mode spectrum of the merged object in that earliest window remains, with current detector sensitivity, incompletely characterized. This gap matters enormously. The next generation of gravitational wave observatories, the Einstein telescope, planned as a triangular underground detector in Europe with arm lengths of 10 kilometers, and the Cosmic Explorer, a proposed American facility with arm lengths of 40 kilometers, are designed to achieve sensitivity levels 10 to 100 times greater than current LIGO. At that sensitivity, the early ringdown signal will be measurable with sufficient precision to distinguish between a Kerr black hole and a gravastar across a much wider range of model parameters. The second observational frontier opened not through gravitational waves, but through light. The Event Horizon Telescope, a global network of radio observatories operating together as a single Earth-sized interferometer, released the first resolved image of the shadow of a supermassive compact object in April 2019. The target was the object at the center of the galaxy Messier 87, located approximately 55 million light-years from Earth, carrying a mass of approximately 6.5 billion times the mass of the Sun. The image showed a bright asymmetric ring of radio emission surrounding a central dark region. The ring's diameter matched the prediction of general relativity for the photon sphere of a Kerr black hole of that mass to within the measurement uncertainties. In 2022, the Event Horizon Telescope released a second image. The compact object at the center of our own galaxy, Sagittarius A star, located approximately 26,000 light-years away, with a mass of approximately 4 million solar masses. Again, the photon ring diameter and brightness distribution were consistent with the Kerr metric. Neither image rules out a gravastar. The photon ring of a gravastar with the same mass would be nearly the same size. The distinguishing features: subtle asymmetries in the brightness distribution, the precise width and substructure of the photon ring, the presence or absence of emission from within the shadow, require angular resolution and dynamic range beyond what the current Event Horizon Telescope array achieves. The next-generation Event Horizon Telescope, incorporating additional stations including space-based antennas, is designed to resolve these features. Its expected angular resolution of approximately 15 microarc-seconds, where 1 microarc-second is 1/millionth of 1/3600th of a degree, small enough to read a newspaper on the surface of the Moon from Earth, would make it capable of detecting the subring structure that theorists predict should differ between a black hole and a gravastar. The Brainworld results published in early 2026 added a new dimension to the theoretical landscape. Researchers working within the Stanovsani Brainworld framework, a model in which our four-dimensional universe is a membrane embedded in a higher dimensional space-time, with the extra dimension being time-like rather than space-like, demonstrated the first fully analytic, finite-thickness, stable gravastar solution that does not rely on the idealized thin-shell approximation used in the original Mazur-Mottola model. In this framework, higher-dimensional gravitational effects, described mathematically by corrections to the Einstein equations arising from the bulk Weyl tensor, the part of the curvature tensor that propagates freely through the extra dimension, naturally generate the anisotropic pressures required to stabilize the gravastar shell. The stabilizing mechanism is not imposed by hand. It emerges from the geometry of the extra dimension itself. The active gravitational mass of this Brainworld gravastar is suppressed. In some parameter regimes, it is negative, a direct consequence of the repulsive interior condensate pushing outward against the shell. This is not a violation of energy conservation. It is a consequence of the specific way that dark energy and ordinary matter couple in the modified gravitational framework of the Brainworld. The exterior space-time geometry remains indistinguishable from Schwarzschild at large distances. An observer far from the object measures what appears to be a perfectly normal, massive, compact object, with nothing in the gravitational field to indicate that the interior is a quantum condensate rather than a singularity. What makes this result significant is not just the stability analysis. It is the demonstration that the gravastar solution arises naturally, without fine-tuning, without artificial construction, from a theoretically motivated modification of gravity that was developed for entirely independent reasons. The Brainworld framework was not invented to produce gravastars. It was developed to address the hierarchy problem in particle physics, the question of why gravity is so much weaker than the other fundamental forces, and to provide a geometric framework for understanding the cosmological constant. The fact that it also produces stable, physically viable gravastar solutions is an independent confirmation that the gravastar is not merely a mathematical curiosity. It is a prediction of serious theoretical physics. The observational and theoretical pressures have been converging on the same question from opposite directions for 25 years. The detectors are getting sharper, the models are getting more precise. The parameter space in which a gravastar could hide, indistinguishable from a black hole by every instrument currently operating, is narrowing. And at the center of every galaxy in the observable universe, including our own, something sits quietly at the intersection of general relativity and quantum mechanics, radiating almost nothing, bending light, anchoring billions of stars in their orbits, and does not yet reveal which side of that boundary it stands on. The fourth observing run of the LIGO-Virgo-Cagra network ran from May 2023 to November 2025, 2 years and 6 months of continuous listening. When the collaboration tallied the results, the catalog had grown by approximately 250 new gravitational wave signals, bringing the total number of confirmed detections to roughly 350 events. In a single decade, gravitational wave astronomy had gone from a single historic chirp to a catalog dense enough to perform population statistics on black holes across cosmic history. Each event in that catalog is a data point in the largest stress test general relativity has ever undergone. On January 14, 2025, a signal arrived at the LIGO detectors that stood apart from everything that had come before it. Designated GW250114, it was the clearest gravitational wave signal ever recorded from a merging black hole pair, so clean, so high in signal-to-noise ratio that researchers were able to extract not one, but two distinct tones from the post-merger ringdown with constraints on a third. These tones are the quasi-normal modes, the specific frequencies at which the newly merged object oscillated as it settled into its final Kerr configuration. Every tone matched Einstein's prediction to within measurement uncertainty. The no-hair theorem held. The mass and spin values extracted independently from each tone were mutually consistent. The instrument that recorded GW250114 was operating at a sensitivity 10 times greater than the detector that recorded GW150914 in 2015, a direct consequence of a decade of engineering refinements to mirror suspensions, laser stability, quantum noise suppression, and seismic isolation. A new adaptive optics technology called Frosty, developed to correct thermal distortions in LIGO's mirrors caused by extreme laser power at megawatt levels, is expected to expand the observable gravitational wave universe by a factor of 10 when fully implemented, meaning detectors operating with Frosty-class optics will be sensitive to mergers 10 times farther away, sampling a volume of space 1,000 times larger than current instruments. 1,000 times larger. The observable universe extends approximately 46 billion light-years in every direction from Earth. The current LIGO network is sensitive to binary black hole mergers out to a distance that depends on the masses involved. For systems similar to GW150914, approximately 5 billion light-years. A tenfold increase in sensitivity distance extends that reach to 50 billion light-years beyond the current observable horizon, meaning every binary black hole merger massive enough to produce a detectable signal occurring anywhere in the observable universe from the present back to the earliest epochs of black hole formation falls within the detection threshold. The merger of two black holes that occurred when the universe was less than 1 billion years old, when the first generation of massive stars were dying and collapsing in environments with almost no heavy elements, in conditions that no longer exist anywhere in the local universe, would register on the upgraded detectors. GW231123 was already a herald of that era. Detected during the 04 run, it produced a final merged object with a mass exceeding 225 times the mass of the Sun, the most massive black hole merger ever recorded through gravitational waves. Its parent objects were each so massive that standard stellar evolution models struggled to account for them through single-star collapse alone. Stars that collapse directly to black holes are predicted to have an upper mass limit, the pair instability gap, between approximately 60 and 130 solar masses, where the core temperature becomes high enough to produce electron-positron pairs, draining the radiation pressure that supports the star and triggering a runaway collapse or explosion before a black hole can form. Objects above that gap should not exist as direct collapse products of single stellar evolution. The fact that GW23123's progenitors appear to lie above the gap suggests they were themselves products of earlier mergers, black holes that had already grown through at least one previous collision, accumulating mass in dense stellar environments like globular clusters or galactic nuclei. This is the second generation of black holes, objects that carry in their mass the compressed history of earlier violent events, whose gravitational wave signatures bear the imprint of previous mergers encoded in their spin parameters and mass ratios. Detecting these objects and characterizing them statistically requires exactly the kind of catalog density that 04 has begun to provide. The LISA mission, the Laser Interferometer Space Antenna, will operate in a regime complementary to ground-based detectors in a way that transforms the observational landscape entirely. LISA consists of 3 spacecraft flying in a triangular formation with arm lengths of 2.5 million kilometers, 2.5 million kilometers, a distance equivalent to approximately 6.5 times the average distance between Earth and the Moon. The triangle orbits the Sun in a formation trailing Earth by approximately 20 degrees. The gravitational wave frequencies LISA is sensitive to, between approximately 10 to the power of -4 and 10 to the power of -1 Hertz, are far below the band accessible to ground-based detectors, opening an entirely different population of sources. the inspiral of stellar mass black holes into supermassive black holes at galactic centers, occurring over years or decades, the merger of supermassive black hole binaries with masses in the range of 1 million to 10 billion, solar masses, and potentially the gravitational wave background left over from cosmological phase transitions in the early universe, ripples in space-time generated fractions of a second after the Big Bang. The inspiral of a stellar mass object into a supermassive compact body, an extreme mass ratio inspiral in the technical vocabulary, is where the Gravastar question becomes observationally acute in a way that no current instrument can match. As a stellar mass black hole or neutron star spirals inward toward a supermassive compact object over thousands of orbits, the gravitational wave signal it emits is an extraordinarily precise map of the space-time geometry it is moving through. Every deviation from the Kerr metric, every perturbation to the clean rotating black hole geometry, imprints itself on the phase evolution of the gravitational wave signal across those thousands of orbits. Tiny differences accumulate. Deviations that would be invisible in a 0.2 of a second ring-down become measurable distortions in a signal that spans years. If the central object is a gravastar rather than a black hole, the extreme mass ratio inspiral signal will diverge from the Kerr prediction at a level that LISA is specifically designed to detect. The orbiting compact object will, at some point, approach the surface of the gravastar shell, a surface that does not exist in the black hole model. The shell will absorb and reprocess the radiation from the infalling object in a way that differs from the way an event horizon does. Some of that energy may be re-emitted. The tidal coupling between the inspiraling object and the shell material will alter the orbital evolution in ways that leave precise, calculable signatures in the gravitational wave phase. LISA's sensitivity to phase evolution across millions of wave cycles will make these signatures detectable, or their absence will push the Gravastar parameter space into regions so extreme that theorists will be forced to confront entirely new constraints. The Milky Way's own central object, Sagittarius A*, is a 4 million solar mass compact body that has been tracked with extraordinary precision by the gravity collaboration at the Very Large Telescope Interferometer in Chile. The orbital parameters of the star S2, which completes a full orbit around Sagittarius A* in approximately 16 years, have been measured to sufficient precision to detect both the relativistic precession of the orbital periapsis, the point of closest approach rotating forward in the direction of orbital motion, just as Einstein's theory predicts, and the gravitational redshift of S2's light as it passes through the deep gravitational well near closest approach. Both measurements are consistent with the Kerr metric. Neither rules out a gravastar. The star S29 passed closer to Sagittarius A* than any previously tracked object in 2021, reaching a periapsis distance of approximately 100 astronomical units. 1 astronomical unit being the average distance between Earth and the Sun, approximately 149,600,000 kilometers, while traveling at a speed of approximately 3% of the speed of light during closest approach. The relativistic effects on its orbit were measurable. They matched general relativity. In early 2026, the Gravity Plus upgrade to the Very Large Telescope Interferometer came online, improving the sensitivity of the near-infrared interferometric imaging by a factor of approximately 4 and extending the limiting magnitude, the faintest objects the system can track, sufficiently to monitor dozens of stars in the innermost parsec around Sagittarius A* simultaneously. 1 parsec equals approximately 3.26 light-years, or approximately 3 times 10 to the power of 16 meters. The innermost parsec around Sagittarius A* is one of the densest concentrations of massive stars in the observable galaxy. Tracking their orbits with gravity plus precision will, over the coming decade, accumulate a gravitational map of the central object's space-time geometry at a level of detail that no previous instrument could approach. The 5th observing run of LIGO Virgo Kagra, 05, is scheduled to begin in late summer or early autumn of 2026. It will incorporate the sensitivity improvements developed since 04 concluded. The catalog of detected events, already at 350, will grow by hundreds more. Among them, statistically, will be mergers with properties that strain current models, objects in the pair instability gap, asymmetric mass ratio systems, events with ring-down signatures that depart at some level of significance from the clean Kerr prediction. In February 2026, the signal GW250114 was published with the most stringent tests of general relativity ever conducted from a gravitational wave event. The ring-down was measured at a precision that allowed 3 quasi-normal mode tones to be characterized. All 3 matched. The no-hair theorem held at the tightest constraints ever established from a single event. Every test passed. And yet, in the same paper, the authors noted that general relativity cannot be the final theory. It does not explain dark energy. It does not explain dark matter. It does not reconcile with quantum mechanics at the Planck scale. The tests confirm the theory within their precision limits. They do not confirm it beyond those limits. And the precision limits of GW250114, the sharpest gravitational wave signal in history, are still orders of magnitude away from the scale at which quantum gravitational effects are expected to appear. The universe is passing every test we give it. The tests are not yet hard enough. Every detection adds one more decimal place to the confirmation of a theory that every physicist knows cannot be complete. The ring-down of GW250114 said, Kerr, to the precision of our instruments. Not, Kerr and nothing else is possible. The difference between those two statements is the entire open frontier of physics, the space in which Gravastars and every other proposed resolution to the singularity problem must either survive or be eliminated. 350 confirmed mergers. Each one a collision between objects containing the compressed remains of massive stars or the accumulated mass of earlier mergers, falling together across distances measured in billions of light years, converting solar masses of energy into space-time ripples in fractions of a second, the most violent events the universe produces after the Big Bang itself. And each one, after the fury of merger, settling into a quiet final object that emits almost nothing, that sits in its host galaxy, bending starlight, anchoring stellar orbits, and declining to reveal whether its interior is a singularity or a quantum condensate of dark energy, with a surface cold enough to make the cosmic microwave background radiation feel warm by comparison. The detectors are running, the catalogs are growing. The next generation of instruments will be 10 times more sensitive than anything operating today. The universe has been keeping this secret for 13.8 billion years. It will not keep it much longer. 10 years ago, on the 10th anniversary of the first gravitational wave detection, physicists gathered in London, in Rome, in Pisa, and in Frankfurt to mark what had happened to their field. The celebrations were not ceremonial in the way that anniversaries often are, not the gathering of people congratulating themselves on a completed project. They were working conferences, crowded with data, with unresolved questions, with the specific technical language of people who are still in the middle of something. The Einstein telescope was discussed as the next frontier, LISA as the space-based instrument that would open an entirely new gravitational frequency window. The catalog of detected events, growing toward 350, was reviewed not as a monument to past achievement, but as a data set with gaps in it, gaps that the next generation of instruments was specifically designed to close. That is the texture of physics in progress. Not finished, not even close. The question of what sits at the center of a black hole has been open, in one form or another, since Schwarzschild wrote down his solution on the Eastern Front in 1916. For most of that century, the singularity was accepted as a mathematical prediction, real in the equations, almost certainly not real in the physical universe, and beyond the reach of any instrument to probe. The event horizon sealed it away. Whatever the singularity actually was or was not, it could not affect anything outside the black hole, and nothing outside could reach it. It was, in a practical sense, experimentally irrelevant. Physics could proceed without resolving it. That irrelevance ended in September 2015. The moment a gravitational wave detector recorded the ring-down of a newly formed compact object, the interior of that object became, for the first time in history, observationally accessible. Not directly, but through the imprint of its geometry on the space-time oscillations propagating outward. The ring-down carries information about the structure of the merged object. Not the information locked behind an event horizon, not the quantum states of the matter that fell in, but the macroscopic geometry of the resulting space-time. The quasi-normal mode spectrum, the relationship between the tones, the rate at which they decay. These are not speculative quantities. They are measured. They are compared against predictions. They constrain the space of possible objects. The no-hair theorem, the statement that a black hole is completely characterized by its mass, spin, and charge, is now a testable proposition rather than a mathematical theorem applied to unobservable objects. GW250-14 tested it with 3 quasi-normal mode tones simultaneously. It held. The next event with comparable signal quality will test it again, with whatever incremental improvement in sensitivity the upgraded detectors provide. The event after that will test it again. The accumulation of these tests, across hundreds and eventually thousands of events, is the most powerful empirical probe of the black hole hypothesis ever constructed. And yet, the Gravastar was never the only alternative. It occupies a specific corner of a much larger theoretical landscape populated by objects that have acquired, collectively, the name black hole mimickers, compact objects that reproduce some or all of the observational properties of a Kerr black hole from the outside, while differing from it in their interior structure. Fuzzballs, proposed within the framework of string theory by Semir Mathur beginning in 2001, replace the smooth event horizon with a highly excited string state that fills the would-be interior with a quantum fuzz of stringy degrees of freedom. No singularity, no horizon, but a surface at approximately the Schwarzschild radius radiating information back into the universe in a scrambled but unitary way. Wormholes, solutions to Einstein's equations connecting 2 distant regions of spacetime through a throat, have been proposed as models for what LIGO is detecting. Not merging black holes, but merging wormhole mouths, whose ring-down signatures would differ from Kerr in specific calculable ways. Boson stars, hypothetical objects made entirely of ultralight scalar fields rather than baryonic matter, would produce no horizon and no singularity while mimicking the gravitational exterior of a black hole closely enough to evade current observational constraints. Each of these objects makes predictions. Each prediction is a target. The detectors running now, and the ones being built, are the instruments that will eventually reach those targets, or confirm that the targets do not exist. The Hubble tension, the discrepancy between the value of the Hubble constant measured from the cosmic microwave background and the value measured from local distance indicators, now standing at a statistical significance of several standard deviations, is, at its root, a tension about the expansion history of the universe. Gravitational wave observations provide a completely independent measurement of the Hubble constant using the absolute distance to a gravitational wave source, determined from the wave's amplitude, combined with the cosmological redshift of the host galaxy. The current gravitational wave measurements are consistent with both the early universe and late universe values, but with uncertainties too large to resolve the tension. As the catalog of binary neutron star mergers, which produce both gravitational waves and electromagnetic counterparts, allowing precise host galaxy identification, grows into the hundreds, the gravitational wave Hubble measurement will reach precision sufficient to determine whether the tension is a systematic error in existing measurements or a genuine indication of new physics beyond the standard cosmological model. The standard cosmological model itself contains a number whose physical interpretation remains entirely unknown. The cosmological constant, denoted by the Greek letter lambda, introduced by Einstein in 1917 as a term in his field equations to produce a static universe, then abandoned when Hubble's observations of galactic recession demonstrated that the universe was expanding, then reintroduced when supernova observations in 1998 revealed that the expansion was accelerating, is measured with high precision but understood not at all. Its observed value is approximately 10 to the power of negative 52 per square meter. Quantum field theory, applying the same principles that correctly predict the magnetic moment of the electron to 11 decimal places, predicts the vacuum energy density, the physical origin of the cosmological constant, to be approximately 120 orders of magnitude larger than the observed value. 120 orders of magnitude. That is the largest discrepancy between a theoretical prediction and an experimental measurement in the history of science. It is not a rounding error. It is not a calibration issue. It is a fundamental breakdown of the framework at the intersection of quantum mechanics and gravity. The de Sitter interior of a gravastar is filled with exactly the energy density described by the cosmological constant. The same term in Einstein's equations that drives the accelerating expansion of the universe on its largest scales is, in the Mazur-Mottola model, what prevents the formation of a singularity on the smallest scales. The same lambda, the same physics, operating simultaneously at the scale of the observable universe, 46 billion light-years in radius, and at the scale of a stellar mass compact object, a few kilometers across. Whether this is a coincidence, a constraint, or a deep structural feature of quantum gravity is a question the current mathematical framework cannot answer. No theory of quantum gravity yet exists in sufficiently complete form to derive the cosmological constant from first principles, or to derive the gravastar phase transition from first principles, or to unify these two manifestations of dark energy into a single coherent physical picture. What does exist is the accumulating weight of observation. Rainer Weiss, who shared the Nobel Prize in Physics in 2017 for his contributions to LIGO and the detection of gravitational waves, died in late 2025, just before the 10th anniversary of GW 15914. He had spent decades, beginning in the 1960s, developing the technical foundation that made gravitational wave detection possible. Working through the noise analysis, the seismic isolation, the laser interferometry, the quantum noise limits, in a period when the detection of gravitational waves was considered by many serious physicists to be not merely difficult, but possibly impossible in principle, given the extraordinary smallness of the expected signals. The measurement that his instruments eventually achieved, 1,000th the diameter of a proton, sustained and verified across two geographically separated detectors, was the product of that work. It was also the product of a particular quality of mind that refuses to accept that something is unknowable simply because it is currently unmeasured. That refusal is the engine of all of this. The question of whether the objects LIGO detects are Kerr black holes or gravastars or fuzzballs or something not yet named is not a question that the current data can definitively answer. It is a question that the current data is beginning to constrain. The constraints will tighten, the instruments will improve, the catalog will grow. The quasi-normal mode tests will accumulate precision. The extreme mass ratio in spirals that Lisa will record will map the near-horizon geometry of supermassive compact objects with a fidelity that no current instrument approaches. The next-generation Event Horizon Telescope will resolve the photon ring substructure that current images cannot reach. Somewhere in that convergence of measurements, in the accumulated precision of thousands of gravitational wave events, in the sub-milliarc-second images of galactic centers, in the multi-year gravitational wave phase evolution of stellar mass objects spiraling into supermassive compact bodies, the answer is encoded. The universe has not hidden it behind a veil of principle. There is no physical law that prohibits the measurement. There is only the gap between the precision we have achieved and the precision required. That gap is a fixed quantity of engineering and time. The universe is approximately 13.8 billion years old. The first generation of massive stars formed within the first few 100 million years and collapsed within millions of years of their formation, creating the first black holes, or the first gravastars, or the first fuzzballs, or whatever compact objects the physics of that epoch actually produced. Before the Earth existed, before the sun ignited, before any chemistry complex enough to support observation had assembled itself anywhere in the observable cosmos. Those objects have been sitting in the centers of galaxies, bending light and anchoring stellar orbits and declining to announce their interior structure, for longer than the solar system has existed. They were old when the first photosynthetic organisms appeared on Earth. They were ancient when the first human eyes looked up at the night sky and tried to make sense of what they saw. The human capacity to observe the universe at any precision beyond naked-eye astronomy is approximately 400 years old, beginning with Galileo's telescope in 1609. The capacity to detect gravitational waves, to listen to the universe rather than merely look at it, is 10 years old. The entire science of gravitational wave astronomy fits within a single decade of human history. In a decade, the catalog went from one event to 350. In the next decade, with upgraded ground-based detectors and LISA operating in space, it will grow to thousands, with each event carrying more precise constraints on the ring-down geometry than the last. The parameter space in which a non-Kerr compact object can hide, mimicking a black hole closely enough to evade every current test, is shrinking with every detection. It is not yet zero. It may not reach zero within a human lifetime. But it is compressible, and it is being compressed systematically by the most sensitive instruments in the history of physics. The center of the Milky Way is 26,000 light-years away. The light, and gravitational waves and radio emission arriving at Earth from that direction right now left its source 26,000 years ago, when modern humans were painting cave walls in what is now southern Europe, 50,000 years before the first cities, 100,000 years before the first telescope. The universe communicates across these distances continuously in every form of radiation and space-time distortion simultaneously, indifferent to whether anyone is listening. We built instruments sensitive enough to listen. What we hear in the ring-down of every merger, in the orbital precession of every star tracked around a galactic center, in the photon ring of every event horizon telescope image, is a universe that is consistent with general relativity at every scale we can measure. And that carries, somewhere below our current resolution threshold, the physics that general relativity cannot describe. The singularity, or its absence. The event horizon, or its replacement. The answer to what gravity actually does at the boundary where it meets quantum mechanics. The objects are out there. They have always been out there. They will be there long after every instrument currently operating has been replaced by something 10 times more sensitive, and that instrument has been replaced by something 10 times more sensitive still. The question is not whether the answer exists. The question is only how long it takes us to build something sharp enough to read it.